Hi everyone, my name is Atul. I will be talking about passive interphoton imaging. Since the early days of digital camera sensors until today's state-of-the-art megapixel image sensors, the basic principle of how a camera pixel captures scene brightness has remained unchanged. A camera pixel is like a light bucket. It collects photons for a fixed exposure time. The higher the brightness, the more this bucket fills up. If the brightness is extremely high, the bucket reaches a saturation limit as it cannot hold additional photons. Two things limit the dynamic range: strong noise in dark conditions and saturation limit in bright conditions. This seems to suggest that there is a fundamental limitation to estimating scene brightness if we only rely on the number of photons. Can we do better? The answer is yes. Let's see how. There is an additional dimension to these photons that we have not exploited yet: the time dimension. Let's look at one pixel in this image. We will collect photons for a fixed exposure time. For this darker scene point, there will be very few photons arriving, so the photon arrival timeline might look something like this. Because photons arrive randomly, the gaps between photons will not be the same. We call the time between consecutive photons inter-photon times. Now let's consider a brighter scene point. Again, the interphoton times are random, but intuitively the average interphoton time will be smaller. Finally, for even higher brightness, the average interphoton time will be even smaller. The key intuition is that the pixel brightness is inversely proportional to the average interphoton time. Okay, so how do we measure interphoton time in practice? We use an image sensor called Single Photon Avalanche Diode, or SPAD. SPADs have the unique ability to precisely time tag individual photons. Now, a SPAD pixel does not capture every photon because of a fixed dead time after each photon detection event. Using Poisson statistics, it is possible to computationally account for these photons missed during the dead times and derive an estimate of scene brightness. We call our method InterPhoton SPAD, or IP SPAD. The IP SPAD brightness estimate is given by this simple expression. In theory, there is no saturation limit. In practice, the dynamic range is limited by the time resolution. This plot shows the signal-to-noise ratio of an ideal IP SPAD pixel as a function of true photon flux. In practice, the SNR drops at high flux values due to limited time resolution. The lower the time resolution, the lower the SNR at these high flux levels. We implemented a hardware prototype with a time resolution of 100 picoseconds. This gives over 10 million to 1 dynamic range at the 20 dB SNR level. Let's look at some experiment results. This test scene contains a dark tunnel with a bright halogen lamp outside. A conventional camera requires multiple exposures to cover this extreme dynamic range. Quite remarkably, the eyepiece pad captures the entire dynamic range of over 10 million to 1 in a single shot. You can read the dark text and also see the bright halogen lamp simultaneously. Let's now consider the other extreme. Can eyepiece pads work if we capture very few photons? What if each eyepiece pad pixel only captures one photon timestamp? This will look quite noisy, but the photon timestamps still carry some information. With some denoising, we can reconstruct images with just one photon per pixel. Eyepiece pads can provide unprecedented dynamic range beyond the capabilities of conventional image sensors. This will have implications for various applications, including astronomy, machine vision, and consumer photography. Thank you.